all, whoop, now we're on. First of all, for the lab, I did a little discussion with somebody else on the lab. Another teacher that does physics like all the time, and I asked her about the lab. Because I was just looking at results, and I wrote this lab up, or I stole it and modified it last year, I think, the first time I ran it. So, first of all, your graph, this is not a bad graph. I don't even know. I just found this on the table sitting here. So remember, you should have some force on that spring at the 0, which you do. So if you did the area underneath this graph curve, you could do this, and then you could add this to it. This would be the work done. Now, some group was sticking around. They've got, and it wasn't match up, but that's fine. It seems like this comes out to be about 1 or 1.1 is what I saw on some of them. This comes out to be about 1.1 when you do the work. That area, I think, I don't know, approximately 1.1 or so I saw yesterday in the second group. Then, if you work this out, though, with the change in kinetic energy, you get about 0.41 or something, right? So we're losing this much. We're losing about 50%, which is the inefficiency of the apparatus in creating heat and stuff like that. We're going to do the next lab where we're going to lose 78% of our energy in the next lab. So if you got about 1 for this, but your change in kinetic energy is about 4, that's fine. That seems to be about right. But let's see what you got. I'll look at it and we'll go from there. Okay. Now, let's talk about the quiz then. Yeah, whose is this one? Is this anybody in here? Nobody in here? Looks pretty good. Which one are we doing on this quiz? 18. Uh-oh. Okay. Point B, in order to reach point A, which is 1 meter above the bottom of the swing. Let's go 1 meter. Let's see what we got here. Okay, so I guess we just got it on a string here, huh? It's going to reach point A? All right. Now, let's see. What is the minimum speed? All right, so we need the velocity down here, correct? Up here, if we're assuming that this gets to here and stops, doesn't really say that though, does it? I'm assuming that this has potential energy up here of mgh, and it doesn't give a speed here, so I'm going to say it stops. I'm going to say the kinetic energy probably here is 0. Because the velocity here is 0. And down here, we're going to say the potential energy should be 0 because your height is 0, right?
So is the swing coming from the left at the start, and then when it hits the point B, or is it coming from A and it's going back?
I think the swing is coming down this way. This is like a pendulum problem, the way it looks. I think it's coming this way.
Yeah, I see it is going down. Yeah, I saw a little dotted ball as the swing.
So if we go mgh on top equals 1/2 mv squared on the bottom, cross out our masses, right? We're going to get the square root of 2gh. Would that work? Somebody solve it that way? Anybody? Well, and then H.
You get 4, 4, and
Yeah.
Yeah. So look at it. If we have, let's just say we tied a string to the ceiling, which is one of our labs. Are we doing that lab? I don't know. Or if we have this string right here. If we let this go here, it has, and if my height here is 0, right here's my height 0. If I let this go here, right up here, the velocity is 0. It only has potential energy based upon its height difference, right? When it comes swinging through here, right there, if the height is 0, all of that potential energy is converted to kinetic energy, right? That's all we're saying. Yes. No, it would be a swing. It would be a swing like this. Well, you have force of gravity pulling it down is what's happening, but you're not changing the force. The force of gravity is there the whole time. So it's going to, if you release it from here, it is going to go faster and faster and faster to here. It's going to be maximum velocity, and then it's going to slow down, slow down, slow down, slow down, slow down, slow down, 0. Anywhere in between, it's got both energy, right? It's got energy of motion, and it's up some height.
So with this being 2 times gravity times height 1.
2gh square root, right?
Yeah, so the answer is 4.2.
I hope so. We'll see if,
I was undecided too.
should be
I'll
2gh.
go with 4, 4, 4.
Should be good. All right, what else do we have? What else do we have?
So,
Anything else in this quiz?
yeah, right back on the journey from case I don't know that I've gotten number 6.
6.
Skidding on a straight level road.
All right.
And you go twice as fast, you have 4 times as far.
Well, let's figure this out. So on 6, can't skid anymore is the problem. If you had been traveling twice as fast, what distance would you have skidded under the same conditions? Okay, so let's try to figure this out. We've got some distance here, right? So we know that the work done is going to be equal to the change in. We know that this work is going to be force times distance is going to be 1/2 mv final squared minus 1/2 mv initial squared. So the braking force should be the same. Let's call it 1. Our V final in each case is going to be 0. Right? You're going to come to a stop. So we can get rid of this. Let's let our mass be 1. Let's let our initial velocity be 1. There's our initial conditions, correct? So what's our distance? And our force would be, you could say it's -1 acting opposite, but what's our distance? Who cares what the sign is? What's our distance going to be? If this is -1/2 times 1 times 1 divided by 1, right? Our distance is 1/2, isn't it? Yep. So we'll just do 1/2. Now, the only thing we're going to change is mass isn't going to change. Force isn't going to change. This is going to change to a 2. You don't have negative difference. This would be a negative force, right? This would be a -1, really, because it's acting opposite of motion. So that would be a positive distance. So if you put a 2 in there, you're going to get what number? You get a 2. This number times what gives you this number? Yeah, this number times 4, right? So it should go 4 times. So that's how you can reason those out. Remember, just make them as simple as possible in the beginning. Make them all 1s and double the one they're talking about and make it a 2, or go to 2 to 4 or 10 to 20. All right, what else do we have?
Four.
4, same thing. Okay. Cars, truck is... Okay. Yeah, it's probably the same thing. Then I messed up on those. What else do we have? Anything else? Homework? Do we have one I didn't convert in the answers then? What do we got here for homework? Carrie, did you say there's one of these that... I don't know. What did we have for 4? Okay, 23. I don't know why this has an asterisk. Nah, usually they're a little bit tougher if they have an asterisk, but the initial kinetic energy one half mv squared, right? And then this right here is nothing. This is a scribble. Our kinetic energy is 1/2 mv squared, correct? And then, you know, if you're hitting a nail, it'd be an example. If you're driving a nail into Bob's head with a hammer,
Does anybody think I should file a report?
I do.
Yesterday you said baseball bat. Does it work? Okay. That means you visualize that way too much.
I shouldn't be recording this now. I'm getting proof I should be fired, right? One of those things where you don't record stuff.
2 weeks off.
Now, if you hit this, obviously it's going to be some force times distance, right? So all of this kinetic energy can go into this work. So this, it should be the same, right? What work can be done by the hammer? That's our definition. Whatever we have for kinetic energy should be going into work. These answers need to be the same. Why is the work negative? Because they're probably going to say that the force is going to be acting, this force of Bob's head is going to be acting opposite of motion in a negative direction, probably. Let's see. Let's see. Right. What work can be done? Probably it's the same way with the friction force. If you're going to change this kinetic energy, if this is positive, it's going to work negative probably. That's why I try to stay away from some of that signage stuff. We don't need this. We know that whatever it has for kinetic energy, that's equal to work. That's the work energy theorem. So whatever you get for this answer should be this answer, but the book has this negative. They're equal, just opposite signs. Yeah. Now we could solve this, and then we could do a distance into Bob's head and calculate the force. That would... which other one in here? 21? Somebody say 21? Okay. Runaway. So for 21, the work is equal to the change in kinetic energy. This is going to come to a stop. This is 12 meters per second, and this is 400 kilograms. Oh, so you get 28,000. Yeah, they have a kg. Yeah. Yeah. All right, anything else we have? This would come out to be negative, according to our equation. Yep. What else do we have? All right, let's talk about power. That'll finish us up. Power is pretty simple stuff. So, I'm not going to do a bunch of this conservative, non-conservative. Just these. We should be over here then on this one, mechanical energy and conservation. On this slide, this is just total energy, isn't it? Big E, kinetic plus potential. That's all we're really talking about. Nope. This is just total energy. And the next slide is already something we've already done, talking about energy here. So if we look at this slide, if you're going to drop this rock, the initial velocity is 0. All it has on top then is potential energy, right? Because your kinetic energy is 0. Then anywhere in between, it has both energies, correct? As long as it's up some height, anywhere in between, it has kinetic energy plus potential energy. What is that value going to be? In this case, if it's 3 meters, does it give us a mass? It doesn't. Whatever we get for the energy here of potential, let's say this is 10. This total here is going to be 10, right? It's 10 everywhere, conservation of energy. And at the bottom, our potential energy is equal to 0, right? It only has kinetic. It actually gives us the values that work. So apparently if we plug all these in, we're going to get the same number, right? Because it's at some velocity right before it touches, right? Well, let's calculate this. MGH. Let's just say the mass is 1. If the mass is 1, 9.83. $29.4, right? 29.4 here. Okay. Right here. What is our potential energy? It's 1 meter high. 9.8 joules. Well, if that's 9.8, what's our kinetic? In 0.8, right? Because it has to be the same. So that would get us 19.6. Right? Yeah. I said the mass is 1. Yeah, we're just using 1 for a mass. It's off by that much? That makes me mad. This total should be 29.4, right? Okay. Within the rules of sig figs, this has to be 29.4. So let's see if we did 19.6. What do we get? So our velocity should be what? So if that's equal to 1/2 mv squared, yeah, this is 6.2. This really, if you did it exactly, would be 6.26 meters per second. And then it would come out perfect. Now at the bottom down here, the potential energy is 0. What's our kinetic energy? What's our kinetic energy? At the bottom? What's our kinetic energy at the bottom? No, we don't. 29.4, right? We don't have to calculate it. Whatever it has for energy at the top, that's going to be the energy at the bottom. Right? Right before it touches last millimeter. Conservation of energy. If you start out here at 29.4, you're going to have 29.4 joules of energy everywhere. Anything in between. Same way with our roller coaster problem on our homework. Yeah, because it's on the last page. So for 6.3, you're assuming that this goes over the hump and you just have something like this. Where this is 100 feet. So if we take 100 divided by 3.281, we get 30.5 meters. Yeah, 763. Yeah. Now, for 768, so we're looking for the velocity here in 63. Let's see what we got. So we're saying the roller coaster goes through a low point, barely makes the next hill. If it barely makes this hill, Barely makes the next hill. What can we assume?
Some fat.
What can we assume the velocity is right here? If it barely makes it, it's going to, yeah, the velocity here is going to be approximately 0. We're looking for what the velocity is down here. So the solution's the same. Can I write this out? Okay, so on top here, this potential energy is going to be mgh. The kinetic energy is going to be 0. Down here, our potential energy is going to be 0. Why is our potential energy 0 down here? Because our height is 0, right? Our height is 0. And down here, your kinetic energy is going to be 1/2 mv squared. Might be. Okay. The only thing we have left to talk about is this. Now, if, don't write it, just, if you have a pallet here of, I don't know, cement blocks, and you have to get them up these stairs, whatever, up to here. We're going to put all these cement blocks up here. One person can do it in 5 minutes. One person can do it in 5 hours. They do the same amount of work. Same amount of work. Right? They're moving the same objects up. But what we need to talk about now is simply power, which is work divided by time. Done. Now, typically we say horsepower. So back in the day, if you will, if you've ever been to a rock quarry and seen a big cliff in a rock quarry, when I went to school, that's where all the parties were, in the rock quarries. I don't know. I'm sure that's old school. Nobody does that anymore. I don't know. So it would make sense that if you put a big pulley here, don't write this down, of course. Put a big pulley here. We'll hook this onto a horse. Nope. Well, I don't know what kind of horse this was, but here's my horse. And obviously, you know, how much can that horse lift? Somewhere, somebody actually had to do that, did they not? Where did they define a horsepower? You know, hook something up like this, how much can a horse lift?
So then should they fighting against gravity?
Sure, this is the simplest way to do it, huh? How much can that horse, and then if you did this with enough horses and averaged it out, you can kind of come up with the horsepower. So 1 horsepower is 746 watts. I don't know if that's going to come up, but let's see. So horse or power is just work divided by time. Now, so power just work divided by time, and we still know that so this is going to be in joules, time is going to be in seconds. So we'd have joules per second, which is a watt. Now, here's an interesting one if we write this out. If power is work divided by time, How do we do work? Force times distance divided by time. But what is this? Yeah, that's velocity. Average velocity, yes. So if you know the power, and the force, you might be able to calculate a velocity. Yes. Yes. Average velocity. All right. Let's call that good. You can finish up your homework and your quiz. Let's go. Let's see. Nothing else. Yeah, nothing else. Let's go on and talk about Chapter 8. So Chapter 8, we're going to talk about impulse and momentum, and conservation of momentum, just like we did conservation of energy, elastic, inelastic impacts or collisions. So we've talked a lot about forces, but we haven't talked about the amount of contact time with that force. So this is impulse. Impulse, force times the time interval in which it acts. So for impulse, this would be a Newton. This obviously should be seconds, right? An example of this, a simple example. You've maybe watched slow-mo videos of a baseball bat, a baseball, softball, slow motion softball. That thing gets flattened out a lot, right? If you've watched any slow-mo at all. How much time is this in contact with the bat? How much force is applied for an amount of time? Now, and we're really talking about follow-through as well. If somebody says, oh, you got to have more follow-through, aren't you increasing, a lot of times you're increasing your contact time, right? Here's another example of that. Let me see if I can find it real quick. Maybe I didn't spell that. Let's see. Here's an example. Old movie. Let me fast forward this. Here's his gun. Extra 4 inches, right? So the gas pushing that bullet from behind is going to act for a longer amount of time, right? Simple example of that. So now, let's see. Now, so impulse, force times our contact time. This is impulse. What's that? P is momentum. Now, momentum is, P is my momentum, M is my mass, V is my velocity. So just like I did change in kinetic energy, when we did change in kinetic energy, what stays the same? Mass stays the same, right? When we did change in kinetic energy, we said this is 1/2 m. We could factor out, and this was V final squared minus V initial squared, right? Constant mass. So now, if we do change in momentum, P like this, this would be momentum final minus momentum initial, right? What is momentum? Mass times V final minus mass times V initial. Momentum is mass times velocity. If mass is constant, just like previously, we can factor it out, and our change in momentum really becomes mass times V final minus V initial, doesn't it? Now, this is what we have for impulse momentum theorem. It's just saying this. And I've got it right here. I'm gonna put it this way though. These are equal. Change in time, the amount of contact time. So if you apply a force over a time interval, shouldn't you be changing the velocity? So you're changing the momentum? Likewise, if I say, well, I change my velocity, you're accelerating or decelerating, you're applying a force over an amount of time, aren't you? These are equal to each other. Impulse momentum theorem. Now, if we take this farther from Newton's second law, F equals ma, this is acceleration is change in velocity over change in time. This seems to be missing the m right here. It would still be here. V final minus V initial over their change in time. And if we solve this, this part up here isn't this part up here our change in momentum? Right? This part right here that is our change in momentum. So this comes out of Newton's second law, F equals ma, and this is our impulse momentum theorem. So how you'll see it is like this. Oh, for momentum by itself, momentum is mass times velocity, so kilograms times meter per second. So you'll see this like this. So these have to be equal units. Let's do that. This is how you're going to see it. So that means these units have to be equal, correct? So let's figure this out. Let's do our units then. This is going to be a Newton second, isn't it, on this side? Newton second. On this side, what are we going to have? We're going to have kilograms times velocity, right? Kilograms times meters over seconds. What's a Newton equal to? How do you, right? When you think of Newton, think Newton's second law. How do you get force? Mass times acceleration. And mass times acceleration would be kilograms times meter per second squared, right? But we still have this second here. So these match because this second here is going to be canceled out with one of these, right? So our units should work out. Okay. So on the next page is our baseball. It does give us our baseball example. And it actually does. It shows us a little graph like this for the force. On the next page, if you did 3 per side. And this would make sense. You first do a little bit of contact. This maximum force up here would be when that baseball's flattened the most, right? Then the baseball, golf ball, all these things are going to flex back. Does that make sense? The force is going to change. This is a maximum flatness. That's an example down there. Let's go in order then if we do this. So if we do the top one here, this is example 8.1. Football player in football. Let's do 8.1. It looks like we need to do this baby up here. What do we got here? Calculate the momentum, 110 kilogram. .110 kilogram football player running at 8 meters per second. Well, this is a simple plugger, I hope. Momentum. Mass times velocity. We just plug this in. We get 880. Yeah. Yep. You can't simplify this because these are your base units, mass, distance, and time. So you can't break that down. So it says to compare the player's momentum with the momentum of a hard thrown .410 kilogram football that has a speed of 25 meters per second. I don't know if that's Brett Favre's speed. If people know who Brett Favre is anymore. I don't know what he's been doing. We'll just plug this in. What do we got? .410 kilograms. It's the same thing. The speed of this football, though, 25 meters per second. If we divide this out, you know, this is about 86 times more. Okay, in example 8.2, Venus Williams. I did go to a women's tennis match one time. It was up in the cities. I don't know. My mom was married to Dr. Springer from Durham for a while, and when he took me to this tennis match, let us see that serve coming at him and return it is unbelievable. The fact that another one is, if you think about that tennis ball is coming so fast. Another one is like fast pitch softball, where the person is winding from underneath, coming around at 100 miles an hour with a softball, and they're closer. The softball's 60 feet, baseball's 90. The fact that you can hit that dang softball in fast pitch is amazing too. But the tennis serves, I don't know how. I can't even see the darn things. Yeah. Yeah. It's still amazing. To miles per hour? There's 1.62 kilometers in a mile. Is the easy way to do it. Yeah, this is 130. I've already converted. This is about 130 miles per hour. So 130 miles per hour, what's a tennis court line? From the net to that first box is how many feet? Is it 10, 12, 15? Who's a tennis player? You know what I mean? Well, no. So my question is, so here's the net of a tennis court, right? And then you've got this divided like this, right? I mean, what? So they're standing here, I guess. What is this distance? Is it 60 feet on each side? No. 60, I bet it. You know, think about a softball pitcher 60 feet away. It seems like it's about 60. So this thing's coming at you. It's coming over the net at 130 miles an hour in a distance of 60 feet. I mean, what's the reaction time to actually move your racket and return that is? Half a second? It's 40. This is only 40 feet. Okay. Wow. That's probably right. Okay, we'll quit here. We'll talk about this next time we meet. So we're bubbling next time, and then we're doing collisions, momentum.